Okay. We just got to finish up this last section here, and then we're going to go to chapter 21. Reactions of carboxylic acid. So I'm not having the chat open today, so I got to focus. Reactions of carboxylic acids can be grouped into the four categories indicated in this figure. Of the four, we've already discussed the acidic behavior of carboxylic acids, so deprotonation. We mentioned treatment with LAH. So LAH reduces a carboxylic acid. Okay, so yeah, so this is like LAH. It's a reduction thing. The remaining two categories are examples of fundamental carbonyl group reaction mechanisms: nucleophilic acyl substitution and alpha substitution that will be discussed in chapter 21 and 22. How might you prepare 2-phenylethanol from benzyl bromide? Um, I think you can. I mean, one obvious thing we can do is you phenyl uh, Br, and we can react this with CN or NaCN, which would give us phenyl, 2 carbons, and then N. And then we can react this with acid, which we don't know the mechanism of yet. We get phenyl. We get a carboxylic acid. So we get yeah, how do you name these? These they didn't really give us enough naming. Like, what do you call this? So we have yeah, we're actually almost there. If I get rid of this. Phenyl acetic acid. Is that the IUPAC? Two phenyl ethanoic. Okay, yeah. So 2-phenyl ethanoic acid. Okay, and then you reduce it with LAH. This seems like an insanely overpowered way to, or like, so here, do we have a way to oxidize it? Don't we have, can't we turn this? Yeah, so we can use DMP to take a terminal primary alcohol So first we're going to add DMP. And we're going to get and this is going to be I think this is called cyclopentane carboxylic acid. One of my least favorite names that I've come across. And then once we have that, though, oh wait, I actually don't know what we do. I don't know how to do that one. This is problem 11. Nice. Okay, so I got this bottom one, but we could have also done the Oh, right. I forgot about this. We have a special reagent called PBr3. And I remember going over the mechanism before an exam, but I didn't learn it that well. And then once we have a bromine, we can just do our standard route. Okay, so this is kind of a way that we can really do a lot, actually. This is a pretty powerful. All right. Nitriles are analogous to CAs in that they both have a carbon atom with 3 bonds to an electronegative atom, and both contain a pi bond. Thus, some reactions of nitriles and carboxylic acids are similar. Both kinds of compounds are electrophiles. For instance, and both undergo nucleophilic addition reactions. Nitriles occur infrequently in living organisms, though several hundred examples are known. Cyanocycline A, for instance, has been isolated from the bacterium Streptomyces levandulae and was found to have both antimicrobial and anti-tumor activity. In addition, more than 1,000 compounds called cyanogenic glycosides are known. Derived primarily from plants, cyanogenic glycosides contain a sugar with an acetyl carbon. Acetyl carbon. I don't know what that means at all. Is there a figure for this? I don't even know what the heck they're talking about. Okay, whatever. But so it does occur, you know. The simplest method of nitrile preparation is the SN2 reaction of some with a primary or secondary alkyl halide. Another method for preparing nitriles is by dehydration of a primary amide. Okay, so one is just SN2 on but a second way is dehydration of primary amide. An amide RCONH2. Thionyl chloride is often used for this reaction. So the mechanism is we have some carboxylic acid, or no, some primary amide. Then we have S double bond, or no, single bond Cl, Cl, O. So this is the thionyl chloride. And what happens is that the lone pair dumps into a pi from carbon that kicks off this to come attack the sulfur, which pushes a lone pair onto the thionyl oxygen. So now you have R, C, O, S, O minus, Cl, Cl, NH2 plus. And then what happens is this lone pair comes in, dumps back into a pi, kicks off a chlorine, and then that makes a R, C, N, H plus O, S, double bond O, Cl. Yeah, let's draw it like this, Cl. Okay, and then we have a Cl minus, or B. And a base comes and takes this proton. And then we're left with R, C, O, S, O, Cl, NH plus HCl. But then a base again. Really? Does that happen? That doesn't seem like a particularly acidic proton. Plus sulfur dioxide. All right, so here we go. We have their nitrile. Both methods of nitrile synthesis are on an alcohol and amide here are useful, but the synthesis from amides is more general because it's not limited by steric hindrance. Okay. Like a carbonyl group, a nitrile group is strongly polarized and has an electrophilic carbon atom. Nitriles therefore react with nucleophile steel sp2 hybridized imine anions. Oh yeah. Wait, actually, what's happening here? Why does this happen? But I want to see how the ketone forms. That seems weird to me. Oh, here we go. Grignard nitrile. Okay, so they explain it. That's good because I did not understand. Okay, so we can do. So paths in nitriles. We have a nitrile to a ketone by Grignard. We have amine. And then we have amide. And then finally to a Ca. Among the most useful reactions of nitriles is their hydrolysis to yield base catalyzed nitrile hydrolysis involves nucleophilic addition of hydroxide ion to the polar nitrile bond, CN bond, to give an imine anion in a process similar to the nucleophilic addition to a polar carbonyl bond, to give an alkoxide anion. So alkoxides and imine anions are kind of similar. Protonation then gives a hydroxyimine which tautomerizes to an amide in a step similar to the tautomerization of an enol to a ketone. Further hydrolysis gives a carboxylate ion. Oh wow, this is a pretty cool mechanism. All right, let's draw it. Let's do it. So this is the base catalyzed or basic hydrolysis of nitrile. Okay, so first we start out with just some, and then OH minus. And we get R N minus OH. So this is the imine anion. Okay, water protonates the imine anion. So this tautomerizes. Okay, and then this gets discussed later. Oh, this is pretty simple. In, up, down, out. The further the further hydrolysis of the amide intermediate takes place by a nucleophilic addition of hydroxide ion to the amide carbonyl group, which yields in tetrahedral alkoxide. Expulsion of the amide ion NH2- as a leaving group gives the carboxylate ion, thereby driving the reaction towards the products. Subsequent acidification in a separate step yields the carboxylic acid. Okay. Reduction, conversion of nitriles into amines. Reduction of a nitrile with LAH gives a primary amine. Oh, okay, is that it? The reaction occurs by nucleophilic addition of a hydride ion to the polar CN bond, yielding an imine anion, which still contains a C-double-N bond and therefore undergoes a second nucleophilic addition of hydride to give a dianion. Both monoanion and dianion intermediates are undoubtedly stabilized by Lewis acid-base complexation to aluminum species. Facilitating the second addition that would otherwise be difficult. Protonation of the dianion by addition of water in a subsequent step gives amine. Okay. So reduction gives nitrile to amine. So it's going to be some R, C, triple bond N, and we do LAH. Then we're going to get, so let's say that R is, so we get R, C, H, double bond N minus. And this is AlX3. Okay, then LAH again was complexed twice. Wow, that's crazy. Benzylamine. Okay, reaction of nitriles with Grignard reagents. Grignard reagents add to a nitrile to give an intermediate imine ion that is hydrolyzed by addition of water to yield a ketone. The mechanism of the hydrolysis is the exact reverse of imine formation. How did we make imines again? I totally forgot all of this stuff. Mechanism of imine formation by reaction of an aldehyde or ketone with a primary amine. So this attacks this. Hmm. Okay, how would you prepare the following carbonyl compounds from nitrogen? Okay, penton 3-one. This is a different version. They changed it to chlorine. Okay, let's get on to 21, because I think 21 is the more important chapter for my class. Wow. I love these things about the industrial preparation of like all right, we gotta get into the other chapter because I have to do this other stuff. Chemistry is so badass. All right, so what's in this chapter? All right, naming Ca derivatives, nucleophilic acyl substitution reactions, reactions of CAs, chemistry of acid halides, chemistry of acid anhydrides. Chemistry of esters, chemistry of amides, chemistry of thioesters, and acyl phosphates, polyamides, and polyesters, step growth polymers, and then spectroscopy. Closely related to CAs and nitriles discussed in the previous chapter are the carboxylic acid derivatives, compounds in which an acyl group is bonded to an electronegative atom or a substituent that can act as a leaving group in the nucleophilic acyl substitution reaction we saw briefly previously. Acyl group is R. Four most common Ca derivatives are acid halides, acid anhydrides, esters, and amides. Acid halides and acid anhydrides are used only in the laboratory, while esters and amides are both common in laboratory and biological chemistry. In addition, Ca derivatives called thioesters and acyl phosphates are encountered primarily in biological chemistry. All right. All right, naming carboxylic acid derivatives. Acid halides. Acid halides are named by identifying the first acyl group and then the halide. The acyl group name is derived from the carboxylic acid name by replacing the ic or acid or oic acid ending with oil, or the carboxylic acid ending with carbonyl. To keep things interesting, however, IUPAC recognizes 8 exceptions for which an "il" rather than an oil is used. Formic, acetic, so formyl, acetyl, propionic? What the fuck is that? I thought it was propanoic. Propionyl, butyric, butyrol, oxalic, malonic, malonyl, succinic, succinyl, and glutaric, gluteryl. So acetyl chloride. Oh, that's going to be brutal. Okay, let's write this down. So we typically, for acid chlorides, acid chlorides, acid halides. We locate the acyl group, name it, and replace the oic acid with oil. So instead of acetyl, you'd say ethanoil. Okay, so yeah, so you could call acetyl chloride ethanoyl chloride. So another case of this, let's do this one. C to 1OBr. So here, the the original thing is we have a phenyl, a C, a double bond O, and an OH. This is called benzoic acid. So then this is called benzoyl bromide. Okay, cool. All right, now here's where it gets a little bit weird. We have a psi COCl. So we want to name this, so we find the acyl group. So this, I think, is called cyclohexane carboxylic acid. And so in the case of the carboxylic ending, this suffix goes to carbonyl. So then this is called cyclohexane carbonyl chloride. I swear these substituted cyclohexanes and non-conjugated rings are like, bro, I don't know what it is, but those names stink. They're just so long. I don't know why all of the ones on the cyclohexanes are so long. Okay. Acid anhydride. RCO2 COR prime. Symmetrical anhydrides of unsubstituted what does that mean? Symmetrical anhydrides of, so first of all, let me just draw my prototypical anhydride. Okay, I don't exactly understand what they mean by unsubstituted monocarboxylic acid. But in any case, these names make sense. Unsymmetrical anhydrides, those prepared from two different carboxylic acids, are named by listing the two acids alphabetically. Okay. Okay, so here's an example. Okay, so we have acetic benzoic anhydride. That's pretty cool, actually. All right, here we go. Esters. Esters are named by first identifying the alkyl group attached to oxygen and then the carboxylic acid, with the ic ending, acid ending replaced by 8. So oic acid goes to 8. All right, so we have this is ethyl acetate because this goes from acetic acid to acetate. All right, that makes sense. Dimethyl. If you just look, wait, but this one's kind of weird, right? Look. Oh, here we go. Wait, do we have a? No. Oh wow. Okay, but we gotta write this one down. This one's weird because it's got the carboxylic acid, so the ic acid carboxylic ic goes to 8. Huh. This one's weird though, the middle one. So here, yeah. So here we have dimethyl malonate. Yeah, okay. So this is called tert butyl then so the original thing, so let's just look at that. So this goes like this. So this is called cyclohexane carboxylic acid. So then this is going to be called tert butyl cyclohexane carboxylic, so ilic carboxylate. Tert butyl cyclohexane carboxylate. All right. Okay, amides. Amides with an unsubstituted NH2 are named. Oh, are we gonna get into the NN? Oh, fuck yeah. You see this all the time. I always thought this was weird. Amides with an unsubstituted NH2 group are named by replacing oic acid. Okay, so all right, so simple one. This is going to be called, so this is acetic acid. So acetic acid goes to acetic amide. Or no, it goes to acetamide. This part goes to Acetamide. Okay. Acetamide. What do we have here? 1, 2, 3, 4, 5, 6. 2. 6. Okay, so this one is going to just be called, so we have hexanoic, which turns into hexanamide. Hexanamide. Okay, that's cool. Now this one's probably weird. Cyclopentane carboxamide. Okay, that's pretty simple. So the base is carb acid. So then this is going to go to carboxamide. All right, so that's the simple rule. What's the harder rule? If the nitrogen atom is further substituted, is there a notion of a cis or a transimine? Presumably there is, right? Ugh. I feel like the answer's got to be kind of yes, that there's an easy. Yeah, so there's an easy thing. Damn you, Germans! All right. If the nitrogen atom is further substituted, the compound is named first by first identifying the substituent groups and the parent amide. The substituents are preceded by the letter N to identify them as being directly attached to nitrogen. Bro, I feel like this is so goofy. I like how come this smells? Like how can we intuitively feel like, okay, this smells? There's something wrong about that. Yeah, like I would want to look at like really big molecules and like try to run an IUPAC. Like, is there a reference? Like, I think that is probably because fundamentally, what is IUPAC? IUPAC is taking a molecule, which is a molecular graph that has actual, it's an attributed graph, meaning it has additional info, not only about the atom types, but about some sort of spatial arrangement of them, so that you can derive stereochemical properties of the molecule. And it's a mapping between that graph and a text string, a list of alphanumeric characters and of ASCII, basically. And the interesting thing is that the IUPAC people do not provide a reference implementation as far as I know. Does IUPAC provide a reference implementation of a name generator? I would imagine it makes sense to have the standard codify in software. And then people can have that's sweet. It would require, yes, a because it's kind of weird. Like, I feel like there's a number of pieces of software that coming from software, you're like, why doesn't this exist? And you would also want, I mean, I don't think that there's names for these exactly. Oh, I've heard of Inchi before, but I didn't know it was one made by the IUPAC people. That's pretty cool, I think. Damn, dude. That's pretty sick. Wow, look at this, dude. That's cool, man. I always looked at Inchis and I was like, what the heck is this? This is cool. What a weird the version. How can they hash this? How can they hash this to 27? It's interesting that it's hashed. Why do they hash it? Like, yeah, do they have wait, why are there three different colors here? Presumably this has meaning. They wouldn't have written this in three different colors if it didn't make like some sort of sense here. Very interesting. Oh my gosh, that's pretty cool. All right, so what should we do? Like biphenyl or something like that? Actually, I don't. Let's just do something fun. What does benzene look? Oh wait, can we do something with stereochem? How do I draw? Ooh, do I have wedges? Wait, how do I? Oh, wow, calculate CIP? Wait, this is sick. That's actually fucking rad. Wait, but so how do I? Okay, here. So I have a wedge. So I want. Wait, but I don't want. I want a cyclohexane. Let's undo this. Okay, so I want a cyclohexane, and then I want like a trans. Let's just do cis for the simplicity of this. All right, so this is uh cis 1,2 dimethyl cyclohexane. It's interesting though, like presumably they had the conversation, hey, how do we like wait, what is R and G? Ooh, Dan. Thanks, Dan. Which Cambridge? That's what I want to know. Oh, the bad Cambridge. Oh wait, but Opsin doesn't even do what I want. Name to structure convert. I mean that's cool, but we want the inverse mapping more importantly. Oh, it's a reaction specification. That's pretty cool, actually. All right, so let's see here we go. So here's the inchy. Here's the inchy key. Okay. So then if I copy this, and then I go to PubChem, and then I look this up, am I gonna get something? That's what I'm saying, dude. I feel like. So, but what if I look up the inchy key then? Wait, but then, oh, see, that's the interesting thing though. Is like I don't know how they're doing this hashing, but for some reason the inchy key did not work, but the inchy didn't work, but the inchy key worked. And importantly, the stereochemistry was right. So the interesting thing about the 1,2 cis is that they're like this. They're like that. Which I always thought was weird because I don't know. Or wait, they're like this. I did it wrong. Okay. So that's good. Alright. I need some water. going on a walk. I'll be back in 10 minutes. All right. All right. So if the nitrogen atom is further substituted, the compound is identified. The compound is named by first identifying the substituent groups and then the parent amide. The substituents are preceded by the letter N to identify them as being directly attached to the nitrogen. So N-methylpropanamide, propanoic, propanamide, N-methylpropanamide. Okay. N-diethyl cyclohexane carboxamide. Right, that one's pretty straightforward. The only thing I need to remember is that, yeah, I actually know that already. Thioesters. Thioesters are named like the corresponding esters. If the related... Oh, I definitely prefer the thioate over the thioacetate. Butane thioate is way better than thiobutaneate. Thioesters are named like the corresponding esters. If the related ester has a common name, the prefix thio is added to the name of the carboxylate. Acetate becomes thioacetate, for instance. If the related ester has a systematic name, the oate or carboxylate ending is replaced by thioate or carbothioate. Butanoate becomes butane thioate, and cyclohexane carboxylate becomes cyclohexane carbothioate. All right, acyl phosphates. Acyl phosphates are named by citing the acyl group and adding the word phosphate. If an alkyl group is attached to one of the phosphate oxygens, it is identified after the name of the acyl group. Benzoyl. What is the rule for oil? We do oil. Let me pull up my chat. Okay. Play this. Fucking what? All right. So oil. Oil was for acid halides. But it's really just the name of the acyl group. So that's what they mean by the oil. A summary of nomenclature rules. Carboxylic acid is an ic acid. An acid halide is an oil halide. An acid anhydride is just anhydride. Amide, O8, thioate, oil phosphate. Okay, cool. All right. I like naming. I feel like I've always liked naming. All right, 21-1. 1, 2, 3, 4, 5. Okay, so we have C, 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 C. Then we have a methyl, C. And then we have a so this should be 4-methyl pentanoic acid, which turns into the same thing but oil chloride. So it should be 4-methyl pentanoyl chloride. Okay, here we go. So we have a cyclo, so just draw psi, C, C double bond O, and H2. Okay, so first off, if we just had psi, C, C double bond O, OH, this should be, I think, 2. Oh, shoot. Wait, is it? 2-cyclohexyl ethanoic. So if we were to go with that, though, then this would be 2-cyclohexyl. And then for amide, I think we just add amide. But the thing is, it's not going to be, it's not ethanoic acid. See, that's if it's like the parent. It's going to be like, because what is this? If we have psi COOH, this is cyclohexane carboxylic acid. But then if you add a carbon in between there, which we have, I don't exactly know how to name this. We need to open up chapter 20. So wait, 4-methyl pentanoyl chloride. So I was right on that. Cyclohexyl. You probably had it, right? Cyclohexyl acetic acid. I feel like they didn't really cover that case. What's up with the theme? Oh wait, that's cool. I hate how long this thing takes. Two cyclohexyl acetic acid. That's okay. So I did get it right. So okay, if you're gonna continue with that though, this would be two cyclohexyl. Then it would be two cyclohexyl ethanamide. Dude, I think the IUPAC naming system is actually pretty bad. Like historically, maybe it was okay, but it's not very good. We could do better. But it's so entrenched that it's like there's no changing that. Okay, so this is one, two, three. Okay, so this. So first we have a 2-methyl ethyl. 2-methyl ethyl. 2-methyl. And then so this would be propanoic. So then it would be propanoate. 2-methyl ethyl, 2-methyl propanoate. Okay. You know, I've been thinking a lot about like layers of software where there really ought to be, or how useful it would be. Propan, yeah, so we could also call this propan 2 ill. 2-methyl propanoate. This is my favorite name. I actually like this name. Wait, what is this notation here? I think that this is just going to be... so wait, how do we name anhydrides actually? To name anhydrides. So this is benzoic acid, right? So then this should be benzoic anhydride, right? So we have a phenyl, C, double one O, O. And then I believe this 2 just means that it's symmetric. So then this would be benzoic anhydride. Did I get it right? Oh, wait, we have way more of these. So, okay, so we have, right, so this is an ester, all right? So now we know it's an ester. So I could do propan 2-ill as the first part. But then what is the name of the carboxylic acid? It's going to be cyclopentane carboxylic acid. So then this is going to go to propan 2-ill, cyclopentane, carboxylate. So I think it's that. Propan. Okay, next one. All right, so here we have another. So here we have another ester, except the ring is the. So this should be cyclopentyl. Um, so this is going to be cyclopentyl 2-methyl propanoate. Let's see if I can get it. My favorite is when I can actually type it in here. So cyclopentyl 2-methyl propanoate. You always get these crazy ones. right. Cyclopentyl isobut. Okay, cyclopentyl 2-methyl pro. Oh, okay, nice. Okay, so here we have an ene. 1, 2, 3, 4, 5, 6. Does this not just look like a key? Wait. Oh no. Oh, this is crazy. This is a set. Okay. 1, 2, 3, 4, 5. Okay, so this is gonna be first off N-methyl. Okay, then the base acid is going to be pent 4-ene oic acid. So then we're gonna have N-methyl pent 4-ene. I still do amide. So it's still amide. So enamide. N-methyl pent 4-enamide. Okay. Pent 4 wait. N-methyl pent 4-enamide. N-methyl pent 4-enamide. Yeah, that's right. That's it. Why is there wedges and dots, bro? I think that's not like important. So this should be okay. So first off, so this is gonna be propanoic acid, but then it's gonna be two hydroxy propanoic acid. But then I think it's gonna be 2 hydroxypropanoyl phosphate. So it's gonna be 2 hydroxypropanoyl phosphate. Two hydroxypropanoyl. Like, why did it just go to mute Shazam? The sources it checks are so funny. Like, why did it go to... Why did it go to a Tina Shea song? Wait, why did it go to that? Can someone please explain to me what led it to... This has got to be this song, dude. What is this? That is very funny. I don't know what led it down that pathway. Oh, there was Stereochem. R2-hydroxypropanoyl phosphate. All right, we're almost done with these names. There's a lot left to do. But I love naming. Naming is just so fun. Wait, so here we have a thioester. So this is going to be ethyl. Now, 1, 2, 3, 4. So it would be butanoic acid. Butanoic acid. But then what we have is we're going to have 2,3-dimethyl butene 2,3-dimethyl butene oic acid. So that, and then the oic acid is going to be, so it's going to be ethyl 2,3-dimethyl butene thioate. Let's see, did I get it right? Ethyl 2,3-dimethyl 2-butene thioate. All right, good stuff. Ooh, now we get to draw. Drawing sucks. Okay, phenylbenzoate. It's hard to check your work when you draw. Okay, so phenylbenzoate. Oh, I know what it is. It's just going to be phenyl. This is phenylbenzoate. That one's easy. N-ethyl N-methyl butanamide. So first up, we're going to draw butanoic acid. So then we're going to write an N here, and then we have a methyl, and then an ethyl. There's N-ethyl, N-methyl butanamide. Nice. 2,4-dimethyl pentanoyl chloride. Okay, we gotta break this down. So we had pentanoyl chloride. Oh, this one's easy. So this is 2,4-dimethyl pentanoyl chloride. Okay. D. Methyl 1-methyl cyclohexane carboxylate. Okay, so what is the base acid? The base acid is we have a Okay. But then we have a methyl here, so this turns into a methyl. And then we have a 1-methyl. Oh, so I think it's actually like this. This is 1-methyl. Or it's methyl, 1-methyl, cyhexbutanoate. Or not butanoate, cyclohexane carboxylate. Ethyl 3. Oh, what the hell is the oxo again? I think oxo is when you have a ketone, but you can't have it as the primary functional group. So we have pentanoate, so but then 1, 2, 3, we have a second ketone thing. Carbonyl, second carbonyl. All right. Methyl parabromobenzene thioate. Ooh, okay. Okay, so we have a methyl here. And then we have a bromothioate. Oh, wait. Okay, so wait, we have a bromo here. Then we have a thioate means that we still have a double bond to oxygen, but then we have an S, and then it's just a methyl. Methyl parabromobenzene thioate. Okay, formic propanoic anhydride. Wait, let me check my answers first because I gotta flip the page. Okay, so we have phenylbenzoate, good. Ethyl, N-ethyl, and methyl butanamide, easy. C2,4-dimethyl pentanoyl easy. Methyl 1-methyl cyclohexane carboxylate, yes. Okay, good. Ethyl 3-oxopentanoate. Yeah, that's right. And then F, this one's going. Oh, good. I got this one right. I'm happy about that. Okay. What am I doing now? G. Formic propanoic anhydride. So, hold on. Formic acid. Okay, that's formic acid. Or methanoic acid. Okay, then propanoic acid looks like this. So here's propanoic acid. So if we want the anhydride, we're going to get HCOO, C double bond O, C, C. Actually, wait, I want to draw this. All right, the anhydride seems fine. Cis 2-methylcyclopentane carbonyl bromide. This is such a niche rule, dude. This is one of those ones that's just like chop it off, figure something else out. Because I think carbonyl. I don't even remember what that is. What is that rule? Okay, let's see. Okay, this one is obviously right. I think that's like if you have. If you're naming the acyl. I think that's like if you want to name the acyl group. Let's see. We just went up and looked. Is this what I'm looking for? I think it might have been in chapter 20. So wait, where's a ring? But these are conjugated aromatic rings. These are not cyclohexane. Anyways, it's not like the most important. But yeah, if you want to name, well, here it is. Carbonyl chloride. Okay. Wow, that took a long time. Okay, finally we can get to some reactions here. Nucleophilic acyl substitution reactions. The addition of a nucleophile to a polar acetyl bond is the key step in 3 of the 4 major carbonyl group reactions. We saw in the chapter on aldehydes and ketones that when a nucleophile adds to an aldehyde or ketone, the initially formed tetrahedral intermediate can be protonated to yield an alcohol. When a nucleophile adds to a carboxylic acid derivative, a different reaction path is taken. The initially formed tetrahedral intermediate eliminates one of the 2 substituents originally bonded to the carbonyl carbon, leading to a net nucleophilic acyl substitution reaction. So in an aldehyde or ketone, we basically just get a tetrahedral product. But here, we do substitution in, up, down, out. In, up, down, out. That's what my prof says. The general mechanism of nucleophilic addition and nucleophilic acyl substitution reaction. Both reactions begin with the addition of a nucleophile to the C-double-O bond, polar bond to give a tetrahedral alkoxide ion intermediate. The intermediate formed from an aldehyde or ketone is protonated to give an alcohol. But B, the intermediate formed from a carboxylic acid derivative expels a leaving group to give a new carbonyl compound. The difference in behavior between aldehydes and ketones and carboxylic acid derivatives is a consequence of structure. Carboxylic acid derivatives have an acyl carbon bonded to a group -Y that can act as a leaving group, often as a stable anion. As soon as the tetrahedral intermediate is formed, the leaving group is expelled to generate a new carbonyl compound. Aldehydes and ketones, however, have no such leaving group, however, and they don't undergo substitution. The net effect of the addition-elimination sequence is a substitution of the nucleophile for the Y group that was originally bonded to the acyl carbon. Thus, the overall reaction is superficially similar to the kind of nucleophilic substitution that occurs during an SN2. But the mechanisms of the two reactions are completely different. An SN2 reaction occurs in a single step by backside displacement of the leaving group, while a nucleophilic acyl substitution takes place in two steps and involves a tetrahedral intermediate. Yeah, there's never a tetrahedral intermediate. There's actually a planar intermediate. Well, yeah. Okay, so what do we have here? Show the mechanism of the following nucleophilic acyl substitution reaction using curved arrows to indicate the electron flow in each step. All right, so we have, let's name this. This should be, so it's benzoic acid, so it should be benzoyl chloride. So we have benzoyl chloride. And then we have methoxide. So what happens is, in methanol, so this lone pair comes, attacks carbon, and pushes a lone pair here. So now we have phenyl, carbon, single bond, O minus, Cl, and then we have OCH3. Right? And we put this down, and then we go like this. Wait, did we get an ester? Oh, we do get an ester. Interesting. Let me just make sure I'm right. Yeah, in, up, down, out. All right. Oh, this is important. This is definitely important. This is covered in lecture. Relative reactivity of carboxylic acid derivatives. Both the initial addition step and the subsequent elimination step can affect the overall rate of a nucleophilic acyl substitution reaction. But the addition is usually the rate-limiting step. Thus, any factor that makes the carbonyl group more reactive towards nucleophiles favors the substitution process. Steric and electronic factors are both important in determining reactivity. Sterically, we find within a series of similar acid derivatives that unhindered, accessible carbonyl groups react with nucleophiles more readily than do sterically hindered carbonyl groups. Okay. Okay, so addition is usually the rate limiting step in new acyl sub reactions. Nucleophilic acyl substitution reactions. So making the less sterically hindered improves the rate. And so we have like a tertiary alpha carbon, a secondary alpha carbon, primary alpha carbon, and a methyl alpha carbon. And we see that the most reactive carbonyl towards nucleophilic acyl substitution reactions is the methyl alpha carbon. Electronically, we find that the strongly polarized acyl compounds react more readily than less polar ones. Thus, acid chlorides are the most reactive because the electronegative chlorine atom withdraws electrons from the carbonyl carbon, whereas amides are the least reactive. Although subtle, electrostatic potential maps of various carboxylic acid derivatives indicate these differences by the relative blueness of the CO double bond O carbons, the carbonyl carbons. Acyl phosphates are hard to place on the scale because they are not often used in the laboratory, but in biological systems they appear to be somewhat more reactive than thioesters. Okay. Okay, so we have amides. So one, we have amides. They're not very reactive. Two, we have esters. Three, thioesters. I wonder why thioesters are more than esters. And then anhydrides, acid anhydrides. And then acid halides. They specifically wrote chloride, which I find pretty odd. But I'm going to copy them. The way in which various substituents affect the polarization of a carbonyl group is similar to the way they affect the reactivity on an aromatic ring toward electrophilic substitution. A chlorine substituent, for example, inductively withdraws electrons from an acyl group inductively withdraws electrons from an acyl group in the same way it withdraws electrons from and thus deactivates an aromatic ring. Similarly, amino, methoxyl, and methylthio substituents donate electrons to acyl groups by resonance. In the same way they donate electrons to and thus activate aromatic rings. As a consequence of these reactivity differences, usually convert a more reactive acid derivative into a less acid. Acid chlorides, for instance, can be directly converted into anhydrides. Diesters, esters, and amides. But amides can't be directly converted into esters, diesters, and hydrogen acid chlorides. Remember, the reactivity order is therefore a way to keep track of a large number of reactions. Another consequence previously noted is that only acyl phosphates, diesters, esters, and amides are commonly found in nature. Acid halides and acid anhydrides react so rapidly with water they can't exist for long in living organisms. Okay. Yeah. Okay. In studying the chemistry of carboxylic acid derivatives in the next few sections. In studying the chemistry of carboxylic acid derivatives in the next few sections, we'll be concerned largely with the reactions of just a few nucleophiles, and we'll see that the same kinds of reactions tend to reoccur. So there's hydrolysis, alcoholysis, aminolysis, reduction, Grignard reaction. All right, so let's just go down the list. So we have an acid derivative, and water will lead to a carboxylic acid. Alcoholysis will lead to an ester. This is interesting. The double. This is like the. This is like the triphenyl methanol synthesis. All right, predicting the product of a nucleophilic acyl substitute. I'm just gonna call them NASRs. NASR reactions. Okay, let's go. Okay, let's go. All right. Predict the product of the following nucleophilic acyl substitution reaction, the NASR, of benzoyl chloride with 2-propanol. Rank the compounds in each of the following sets in order. Rank the compounds in each of the following sets in order of their expected reactivity toward nucleophilic acyl substitution. Okay, so A is already, in order. Here we have an ester. We have an ester, but it's got, I'm going to say 3, 2, 1. Okay. I'm gonna look at the answer for these. I don't really know. Like how I'm supposed to know. Like at this point, am I just supposed to assume that it just does the substitution, or do I need to know more? I'm not exactly sure. Okay, the following structure represents a tetrahedral alkoxide. ion. Intermediate formed by addition of a nucleophile, probably this methoxy group, to a carboxylic acid derivative. I don't see how it's a carboxylic acid derivative. It looks like it's literally just a carboxylic acid. Or it could be that this OH attacks here. So presumably then the leaving group is methoxy and the starting acid derivative is then methyl. Oh, fuck. I already forgot how you... I think it needs to be 2-methyl cyclopentyl. 2-cyclopentyl ethan... Oh, wait. Ethanoate. Methyl 2-cyclopentyl ethanoate. Acetate. Methyl 2-cyclopentyl acetate. And the ultimate product should just be 2-cyclopentyl acetate or acetic acid, 2-cyclopentyl acetic acid or something like that. Let's see. Okay, that one was obvious. That one was obvious. Okay. This is what I want to know. So yeah, so it's just but why here does this not form the acid? I guess methoxide takes the proton. Okay, that one's fine. I'm fine with that one. Okay, that one I'm also fine with, I guess. And that one I'm fine with. Okay, that's cool. The structure represents the tetrahedral intermediate of methyl cyclopentyl acetate. Let's go. With hydroxide, a nucleophile. The products are cyclopentyl acetate anion and methanol. Okay. Yeah, the only thing I'm not really getting is the resonance stuff. All right. The direct nucleophilic acyl substitution. Okay, hold on. New section. Come on. Let's do this. So this is reactions of CAs. So the direct nucleophilic acyl substitution of a carboxylic acid is difficult because hydroxide, or OH, is a poor leaving group. Thus, it's usually necessary to enhance the reactivity of the acid, either by using a strong acid catalyst to protonate the carboxyl and make it a better acceptor, or by converting the OH into a better leaving group. Under the right circumstances, however, acid chlorides, anhydrides, esters, and amides can all be prepared from carboxylic acids by Nassers. Conversion of carboxylic acids into acid chlorides. In the laboratory, carboxylic acids are converted into acid chlorides by treatment with thionyl chloride, SOCl2. Dude, that's a killer reaction. This reaction occurs by Nasser pathway, in which the carboxylic acid is first converted into an acyl chlorosulfite intermediate. Can we get a mechanism? Bro. This reaction occurs by nucleophilic acyl substitution, by the way, in which the carboxylic acid is first converted into an acyl chlorosulfite intermediate, thereby replacing the ammonia. Much better leaving. Yeah, this is what I was remembering. But didn't we get a full mechanism drawing for this thing? Or did I have to look that up? I think I had to look it up. I love these, dude. I feel like they need more of these in this book. Oh, here we go. This is basically it. I actually like this. Dude, this is cool. Dude, this is great. I like this a lot. I wonder how they made this. Like, is it fully automated or like did someone just like all frames are exported directly from the RD kit builder? Is that really what happens? I don't feel like that's exactly what my professor showed. This thionyl chloride stuff is pretty sick though. This is gonna have a good one. I know it. I love these. Okay, so this does happen. Wait, hold on. Where's the mechanism? Hmm. All right, so the pi carbonyl pi attacks the sulfur, and it forms this chlorosulfite ester, and it's prompted by the dumping of the lone pair into a pi. and then it's deprotonated. So that makes sense. Okay, so Cl picks up a proton or something like that. Once the chlorosulfate ester is formed, the acid chloride is formed through a classic addition-elimination reaction. The chloride ion then attacks. So I don't. Well, I don't know about that. The chloride ion then attacks the carbonyl carbon, leading to the formation of a CCl and a breakage of a CO pi. Wait, what the hell? See, this is what I'm saying. It's like, this is that? I don't know. Okay, so let me just write down this mechanism. So we have carboxylic acid, and then we have thionyl chloride, which is SCl double bond O, and then it also has a lone pair. This pi comes in, and then R C O S Cl Cl O minus. This is Cl. Wait, this is not Cl. What the fuck am I talking about? This is OH. Oh, and wait, what prompts this whole thing is that this thing tries to resonance, basically. So this is actually a double bond, and this is an oxonium. Okay, so now we have the oxonium. And then what happens? This minus first has to drop it down, right, and kick off the chlorine. Okay, but now what happened? Now we have plus Cl minus. And Cl minus attacks the carbon. Oh, and this is an H on it. This is a plus, yeah. And yeah, it makes the most sense for it to do this. And then it goes like that. So now we have R C Cl OH OSCl double bond O. So we have this. But now the lone pair on oxygen comes and dives into a pi again. This time the sigma bond here so now we're left with R C double bond OH plus Cl, and then we also have S double bond O minus Cl, and I'm guessing what happens is this feels like this. To get the sulfur dioxide. And then we just have some base. Okay. All right, so this is how we form. So first off, this is how we form or make acid chlorides. from carboxylic acids. Right, so they show a much more abridged form where it's like, okay, first we have this chlorosulfite ester thing, and chloride ion attacks, and then with this negative charge, it dumps back into a pi, and then this sigma goes into a pi. I mean, I actually don't know if this single goes into a double. I don't really know how to say that better. But and then kicks off chlorine, which is what I predicted. Okay. Now it's Ca2 anhydride. All right. Acid anhydrides can be derived from two molecules of carboxylic acid by heating to remove one equivalent of water. Because of the high temperatures needed, however, only acetic anhydride is commonly prepared this way. 800 C? That's actually crazy. There are some weird syntheses of, like that ketene lamp thing. Alright, so that was just kind of a quick little tidbit. Conversion of carboxylic acids into esters. Oh, wait, I need to take a shower. Shoot. Okay, hold on. Let me try to finish this section and then I'm going to finish it up. Oh, it's like the longest section ever. It's so long. Okay, well, I'm just gonna take a shower now then. Maybe I'll probably end it right now. Okay, all right. So that's like a pretty good 3 hours. I probably got 2.5 hours of studying then. So Fisher certification, um, it's a really short. I remember drawing way more steps for this. Isotope labeling experience seems so interesting. I feel like that is like a huge gift to chemistry mechanism studiers. Like to be able to label all the atoms. Thank God for isotopes. Two bromobenzoic acid and propanol. Damn, I'm goated. Oh yeah, acid. Every time I've done Fisher's purification, though, I've always only done sulfuric acid. But okay, I'm out of here. I gotta go.